where we are in the course. We're still looking at data files and indices. So we're still at the bottom of this architecture diagram, and we will continue to talk about different indices today and the coming lecture as well. So let's start doing that. What we will dedicate today's lecture to is the use of hashing indices inside the database engine. You've learned about the hash table or hash map in CS3 or in your data structures course, and I'm sure you've been using it since then, and it's a very interesting data structure. Why? Because we get this incredibly enhanced performance and O of 1 access to your data. And since in the database world we are interested in querying and processing data, I mean by processing, doing an update, doing an insert, or doing a delete as fast as possible. So O of 1 access obviously is a very tempting choice, or specifically hash tables are very tempting choice to use inside the database engine. And indeed, inside database engines there are variations of hash tables that we're going to talk about today that gives you O of 1 access. So let's try to nail things down a bit. So I will start my discussion by arguing why using the traditional hash table you've learned in your early data structures course is not suitable for databases. And I will refresh your memory with the kind of operations we're interested in and what possible solutions we could come up with as a modification to what you have learned before as a data structure called hash tables. How can we modify it so that it suits the database world? So again, to refresh your memory, just like we are on the same page in case you're not remembering what was this all about. This is a data structure, an in-memory data structure that you've learned before. It has various names: hash tables, hash map, hash set. Okay. The idea is when you're actually inserting or searching or looking up a value, you don't go and do a linear scan inside the data structure from beginning to end. Like for example, in the case with the linked list, to find the place where you should insert or find the key that you're looking for. Instead, what we do is we use a hash function, and you pass to the hash function the key, the value that you're trying to insert if you're doing the insert operation, which, if you remember, is called in the hash table terminology the put. So what happens is you get the key, you hash it, which means you pass it to this black box that we're calling the hash function, and this black box has an output, and the output is actually the index in the array where you put this key in. And since you're going to use the same black box, the same hash function in the insert and in the search and in the delete, if you've inserted it and then later on you're trying to search for it or you're trying to delete it, you will find it because it's the same mechanism, it's the same box, it's the same hashing function. So if you pass the hashing function the value 10 and it tells you 10 goes to cell number 1, you're going to go put the 10 there. If later on you're searching for 10, you pass the 10 to the same hashing function and it's going to tell you also cell number 1. So when you go to cell number 1, you will find the 10. Okay. Now the nice thing about this approach is that it is not dependent on the size of the data. And that's why we say it's an O of 1 access, because regardless of whether I have 1,000,000 entries in this hash table or 10 entries, the size is not affecting how the hashing function is actually working. The hashing function is a mathematical computation. It takes the key and will do some magic using the key and produce out as a number the array index where I'm going to put this key in. This is in summary the idea of a hash table. Now let's start thinking, can we actually twist this, or can we actually use this somehow as an index mechanism inside a database engine? So if I'm building a hash table on some column in some table, I will retrieve the values inside this column. I get one by one, and one by one the values, and I will pass each one of those values to the hashing function, consider it as my key, and it will tell me, okay, this will go to this array cell, that will go to another array cell, and so on. So I can pretty much treat the values inside a column as a series of keys that I'm trying to store, and inside each one of those array cells, I will put the key and a pointer to where the row is. So there's nothing preventing us, if you start to think of it, building this from scratch, there's nothing preventing us from following the same mechanism to build an index. Okay, just like we have created a hash table out of a set of values, or stored a set of values inside a hash table, we could store the values in a column inside a hash table. And when we're storing inside the hash table, what we pass is the key and the value. The value becomes, where is this row? Okay, which page on the disk, which row in that page, and this is how basically we can take the idea of a hash table and somehow utilize it to create an index. Now let's try to put things a little bit more solid. What should the value associated with the key be? So, if you have access to the hard disk right away, and you know where is the page, or where is the row inside a page, you can just directly point to it, right? Now, this assumes I have access to the individual sectors of the hard disk, if you like, or the individual space on the hard disk. So I could arrange the buckets one after the other. In other words, the output of the hashing function, when I'm trying to insert the key, the output of the hashing function is going to be the place where I write down the row. So let's say I get, I'm building this from scratch. So I have this empty table, and I have a hash index on a specific column. When I'm inserting my first row in this table, I will grab the value that I'm building the index on. Let's say I'm building the index on column H. So I will grab the value for the H for that user, okay? Let's say it's the value 20. So I pass 20 to the hashing function. So I get out some big number. That big number is going to be the address on the disk where I write the row. Can we do that? Well, yes, we can do it, but there is a catch. Now, what's the catch? The catch is that, let's say I passed the value 20, and I got out as an address on, say, the value 15,200. How can I guarantee that that location on disk is empty, so I can go there and write the new row? You get the idea. Now we have a problem, So using the output of the hashing function, which is, a valid approach when you're just starting to think about it, but suddenly you will realize that actually, it's not going to work that simply, So a valid approach, or the approach is going to be like, I will pass the key to the hashing function, and my output of the hashing function is going to be the address where I write the row on the disk. Okay? That will work, provided one very tough, very difficult to achieve constraint, which is that I have access to the hard disk space, and no one else has such an access. Why? Because if you try to understand how things are stored on the disk, you really can't. You have no prediction. There are many applications running at the same time. Okay, there is the operating system running, and there are other applications that you might be running or that you have been running before, and they stored information on disk, or you yourself might have stored some files on disk. So if the output of the hashing function is address number 15,200, well, you need 15,200 address on the disk to be available, and it could be available and it might not be available because you have stored some other information before, like a video that you downloaded, or the cache for the Chrome browser and so on. So basically, you have no control on where things get stored on the disk unless you write your own file system and you divide the disk into partitions, and you create a partition for the database engine, and you have your own file system that manipulates this partition. Now, if you do that, then yes, for sure, you can map the output of the hashing function directly to specific rows, to specific locations on the disk inside your partition, okay? But if you don't, then this approach, although it sounds like super fast, super simple, and super memory saving, because you really, you're just going to store the keys and you jump directly to where the row is stored on the disk, this actually will not work, okay? So unless you have direct access to a hard disk partition and your own file manager, this simply will be met by the the limitations of the fact that you have other files stored on disk. So here's the second option, which is probably the simpler one, or perhaps this is the one you'll get or you will reach to when you start thinking about this for the first time, which is you create an in-memory data structure, hash table, just like the one you've learned before. And this is what I was describing earlier in 2 slides. And the value associated with every key is basically the address where the row is stored on disk. So now we're going back to the scheme we've seen several times before, where I have the table divided into pages. They are stored on disk. And I have something else, an additional thing, which is the hash table index that has for every key where is the row that has this key on disk. So I have the key and the address where the row is, the key and the address where the row is, and so on. Okay? So this is obviously straightforward utilization of what you have learned before, which is an in-memory hash table. Okay? So here is the idea I was just explaining. So I'm going to get some series of values. Where are the A, B, C, and D I'm getting them from? I'm getting them from the column I'm building the hash index on. So I will hash every one of those values using the hash function to get the location where in the hash table where I store these entries. But what I'm going to do, I'm going to start to introduce what we have discussed before, that I'm not going to think of this simply as just a bunch of array cells in memory, which is what you've learned about the hash tables before. I'm going to think of them as being this internal storage inside the hash table as a set of pages that are stored on disk. Remember, we said everything is paged in the database world. The table is paged and the index is paged. So I'm here numbering the pages instead of the array cells. So every one of those 0, 1, 2, 3 are pages on the disk. Okay? Now, in the output of the hashing function is going to be the page number. So if hashing A is giving me 1, that means A will go to page 1. If B is going to 2, that means or hashing B give me 2, that means B is going to be stored in page number 2. And so on for C and D. So this will be the status after I do this insertion. I have every one of those values stored in some page that belongs to this hash index on disk. Okay? Now, I'm doing this exercise with you just that we start thinking carefully about using, how can we reach to use hash tables successfully inside the database engine. Let's say I would like to now insert E. Okay? So I hash E, and if you remember, again from the data structure course, the output of the hashing function we have no control on. It's going to be some number. Okay? And we will always take the mod of the size of the number of pages we have here, or in the classical hash table, the number of cells in the array, to make sure that you don't get an output that's outside what you have. Okay, so inside this hashing function, I will ultimately be modding 4, so I get an entry between 0 and 3. Okay, as an output. Now, let's say I would like to insert E. So I hash E, and it's telling me that the output of the hashing of E is 1, which means I will go to page 1 and insert the E. Now I run immediately into trouble, because according to my model here, every page holds only 2 entries. Now, I cannot simply insert the E there. Okay? So if we're going to follow this approach, perhaps the only thing we can do here is to create another page, a type of an overflow page where we put the E in. Okay? Now, the implication of adopting overflow pages as part of our strategy is that later on, if we get a get for E or a search for E, so I'm going to pass E to the hashing function. I will still get 1 because passing the same value should get you the same output. Now, I will go to page number 1 and I will load it and I will look inside it linearly. It's a linear scanning. It's going to be A, then a C. It's not an E, but I have to remember that I could have here overflow pages, so I will follow the pointer to this overflow page loaded from disk to find the E. Okay? Now, why are we doing this? Because we cannot simply just make the bucket here or the page bigger. Instead of storing 2, we will store 3 or 4. Okay? So what we're going to do is we will solve the problem using overflow pages. Now, what about deletion if we adopt overflow pages? So if I delete E, that's not an issue. Well, first I have to find it, so I'm going to hash E, and the output of the hashing function is going to be page number 2. I will go to page number 2 and erase it from there. And then F is going to be the same. Okay? Now, I will run into a little trouble here, which is to keep track of what has been deleted. So what I would do is I will put some marker inside those pages to make sure that the entry I'm looking at is not valid anymore. It's just, it's a null entry. Okay? And that's what you see happening here. Now, what if I delete C? Now, if I delete C, well, first, how I'm going to go there, I will hash C. The output of the hash function is going to be 1, so I will load page 1 of this hashing mechanism, and I will find the C inside, and I will delete it, and that will be an opportunity for me to do what we call consolidation of overflow pages, where I take the content of the overflow page and put it inside the main page. Okay? Now, I'm showing you here examples that are a bit simple in the sense that the page has only 2 entries, and obviously in the real hash mechanism that uses what I'm describing here, that's not going to be the case, because we'll be bounded again by the size of the cylinder, and if the size of the cylinder is 64 kilobytes, say, then we will have like lots and lots of these values. We will have hundreds, if not thousands, of these values. Okay? But I'm showing you here an example with only 2. So once I delete the C, then I have to consolidate back the D with the B. Okay? Now we come to the discussion of, will the scheme actually work? Up till now, it looks like it could work, okay? We took the idea of the hash table, and instead of storing the values inside an array in memory, that would be an in-memory data structure, we're trying to make it a secondary storage data structure. So instead of storing the values in array cells, I'm going to store it in pages. So we can imagine that replacing every array cell now with a page, okay? And if the page is full, we can use overflow pages. But here is where the model is going to break. Now remember from hash tables discussion is that in order to maintain the good O of 1 access in the put and the get, you have to track the number of keys you have inserted inside the hash table, and track also the number of buckets you have, or in our case here, the number of pages. And this ratio, which is the number of keys divided by the number of buckets, is going to be called the load factor, or basically the utilization of the hash table. And we told you then that we always like to keep it within certain ranges. Specifically, it needs to be less than 0.75 as a ratio, or if you would like to relax it a bit, just so that we can work the math easier, it shouldn't be more than 80%. Now, what does that mean? If I say 75% or 80%, It means I would like to keep my hash table at most 3/4 full. Because if the number of keys is 7, and let's actually put another example. If the number of keys is 50, and the number of buckets is 100, okay, then I'm here assuming that a bucket is equal to 1 cell. So what I could store in is 100, and what I have is actually 50. So it's half full. Okay? Now, if I have 25 keys and what I can store is 100 keys, so it's quarter full. It's basically empty. Okay? It's almost empty. Now, if I have 80 or 90 or 99, say, keys, and I can store only 100, that's almost full. So what we're going to do is we're going to say we would like to keep it always at most 3/4 full. And that is a condition for us to get the O of 1 axis. Now, where is that coming from? So actually, when you later on take the analysis and design of algorithms course, we will use randomized analysis as a specific technique in analyzing algorithms. And we will use also amortized analysis, which is another technique in analyzing algorithms, to prove that 3/4 is a valid choice. So what I want you to understand from now is we cannot exceed the load factor. And we have already discussed this before in the data structure course. We cannot exceed the load factor threshold, which is 0.75 or 0.8 if you'd like, if you just like to relax it so that we can work the numbers, okay? But really it's 0.75. When you go to analysis, you will find that the accurate threshold is 0.75, not 0.8. But I'm just here, for simplicity, I'm just assuming it's 0.8, okay? Now, we also said that we are going to have another threshold to avoid wasting space. So if the hash table is less than quarter full, then we're wasting space. It's 3/4 empty. If it's quarter full, then it's 3/4 empty, okay? And here I'm also relaxing it, I'm saying 50%, half, okay? Well, again, we're going to do something. In both cases, when we go above or below the thresholds, the two thresholds, we do something. And this is really where this is where the trouble lies, okay? We are now getting into a very gray area in terms of performance now, okay? What's the problem? The problem, if you recall from your early computer science course, this is how it works. When we find ourselves crossing our upper threshold, which is the 0.75 or 0.8, what we're going to do is we're going to double the number of buckets or array cells. So if I had an array cell of 10 and I was just about to insert my 8th entry, after inserting the 8th entry, for sure I will cross my upper threshold, okay? So to have this threshold preserved, what we're going to do is we're going to create another array of size 20, which is 2n, of size 20 cells. Instead of 10 cells, it becomes 20 cells. And then we take those 8 values and rehash them into the new array of size 20. And after that, we can continue inserting our 9th, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 18th, and then suddenly we run into trouble again, because we are crossing again the threshold of, actually it's after the 15th, we're going to cross the threshold of 0.75 or 3/4 full, because if we have 20 cells, 3/4 full means 15 cells are actually full. And even if it's 0.8, it's going to be just 16 cells full. So we run into trouble again. So what we do, we resize again the hash table from size 20. So instead of having an array of size 20, we will have now an array of size 40. And we take again those values, those 15 or 16 values, and we rehash them into the array of size 40. Okay? Now, as I told you, this is where everything breaks. Why? Because what I'm just describing now, let's put it in a database context. Now, in the database context, what that means is I'm going to read all the pages of the index, of the hash index, the ones we were thinking to build early on in these slides, I'm going to read all the pages to get all the content of the index, and then create double the size, double the number of pages, and then rehash everything in the old pages to the new pages. That's like a lot and a lot and a lot of database, or of hard disk access. So if your index had 200 pages on disk, you are going to create another 400 pages and read the data from the old 200 pages to put them in the new 400 pages. And then later on, when your threshold again is exceeded, when you go above 0.75 or 0.8, you are going to create, instead of 400 pages, you're going to create 800 pages on disk. That's ridiculous amount of disk access, by the way, okay? We're trying to avoid one page access usually in the database world. So if we can do something in 5 disk accesses instead of 6, we're happy. Now I'm going to create 800 pages on disk and read the old 400 pages to get the entries from inside them to put them in the new 800 ones, okay? And again, if my threshold gets exceeded, I'm going to go and create 1,600 pages on disk and read the old 800 pages to get the entries from them and put them in the new 1,600 pages. So again, simply this is not acceptable. We cannot tolerate this kind of performance and this kind of the hard disk access in the database world, okay? We're always assuming, as I mentioned before, that we will have huge tables and we will have hundreds of megabytes perhaps of rows or of entries in a single table. And if we have a schema of 30 or 40 tables and each one of them averages 200 or 300 megabytes, and then we started creating these indices using this way we were thinking in the beginning of this lecture, then you'll end up crippling down the database engine, okay? Especially that hash indices are also very, very tempting to developers to use, because once the developer realizes, oh, I got an index that performs better than a B+3. B+3 performs in log n, and the hash index will perform in O of 1, so they will be tempted to use it. But now you have a problem, which is that the way hash tables work internally, which is doubling the number of pages, or the number of buckets, basically, whether the bucket is an array cell or a page, the number of buckets, once we exceed the threshold, the upper threshold, it's just disastrous. It's not acceptable. It will not give us any performance that we will be interested in, okay? And even though you are going directly to the page, in the case of, the search, so the search is going to be O of 1, but the insertion is going to be from time to time is going to be so slow when you resize that there's no benefit actually from using it, okay? Because one of those operations where you say, I was just describing, where you create 1,600 pages on disk and you read the existing 800 pages to get the entries from them and put them in the new 1,600 pages on disk, that operation will kill the database engine. It will just blow out the performance, okay, and slow down things to the point where database engine is not going to be responsible. So we have a problem, okay? Now, what is the solution to the problem? The solution is to use a variation of hash tables that is tailored to the database needs, okay? So what you have learned before is called an in-memory hash table, or simply a hash table. What we will look at are two variations of hash tables. One of them is called the extensible hashing, or extensible hash table, and the other one is called the linear hash table. And both of those guys will enable us to use hash tables and get O of access as a way of working, but with a modification on how things run internally inside the hash table, so we don't have to do what was called full reorganization of the pages or of the buckets. So let's look at extensible hashing or extensible hash table. There are two key ideas here. The first one is that we are actually going to take the output of the hash function and convert it to binary. And we will make use of the binary values, or of the bits in the binary representation of the output. Okay? And what we're going to do is we are going to not use all the bits up front, but we will use a subset of the bits, and as the extensible hash table gets bigger, we will use more bits. So in other words, we will start, say, by using 1 bit, and then if we need more space, we will use 2 bits of the output, of the binary equivalent of the output of the hashing function. And if we need more space, or the extensible hash table basically is growing, then we will use 3 bits, then we will use 4 bits, then we will use 5 bits, all the way until we consume all the bits. I'm saying here use as I'm referring to something specific you will see soon, but the idea is, the main idea here is that I don't work with the output of the hashing function, I work with the binary equivalent of the output of the hashing function. The second idea is I will not use all the bits in that binary equivalent right away from the beginning, but I will start with a small number of bits, and as it grows bigger, and you will see why, I will be using more bits. Okay? Now, I will always use the leftmost bits first. So I will start with the 0, and then if I need more space, it's going to be 0, 0, which is the one we have here in the slide, and then 0, 0, 1. So now I'm going from left to right in the bits. Okay? And then I will be using 0, 0, 1, 1, and so on. Okay? And then ultimately, I will be using all of them. Now, the second main idea in the extensible hash table, before I show you the actual thing, is that we are going to use a directory, and the directory will be in memory. So what will be not in memory? The buckets of the hash table themselves. Okay? So the buckets will reside on disk, where every bucket is a page, will be on disk. But I will keep in memory a directory that I consult all the time in order to do anything useful inside the extensible hash table. This directory is inside the data structure itself, inside the extensible hash table. Now, the directory is telling me where to go. In other words, which page of the index to load. So the index could have like 10,000 pages. I won't load them in memory all the time. I will keep them on disk. I will keep only in memory the directory. And then if I would like to access a specific index inside, a specific value inside the index, we're not talking about the table yet, I'm saying a specific value inside the index. In other words, I would like to know, say, where is the row whose key is 50 is stored. So I'm going to consult the index to find out where is that row. The information about where is the row is going to be stored in a page that belongs to this index. But to reach to that entry, that page that belongs to the index, to find out where is the row 50 stored, so that I can retrieve this information so that later on I can go and load the page of the table, I will consult the memory directory, or the in-memory directory. That will tell me, okay, go to this page that belongs to the index. I will go to the page and load it, and then inside that page I will find where is the row. I will find the address of the row. Okay? So in other words, there is a level of indirection here. Okay? Instead of going from memory to the table, I go from memory to bucket to the table. Okay? Or I go from directory to bucket to the table. Now, so again, here is the picture I was trying to, a full picture of what I was trying to explain. What you see on the far right are the pages that belong to the table. We said we're going to cut the table into pages, where every page will hold a subset of the rows. And then we are building a hash index on this column that has 22, 30, and 40. So this index, hash index, this extensible hash table, are the thing that appears on the left here. Okay? That is circled with this red circle. Okay? Now, it has two components: the directory in memory and the pages on disk. I go first to directory to find out which page to load from disk, and from that page I will know where is the row. Okay? So where is the row whose entry is 22? Okay. Now, did we gain anything by having this level of indirection? We have this additional thing we're going through to go to the table. Yes, of course, we've gained a lot actually. This way, as long as this directory remains small, we will not be too much concerned with the notion of does the index fits in memory, because actually we don't care anymore because we're keeping it on disk. The pages of the index, which is these two that have a blue circle around them, are on disk. They're not in memory. So regardless of how big the table is that we're building an index on, or because it's kind of related. The table could have 700 million rows. If the column we're building the index on is unique, that means we will have 700 million values that we're using in building the index. Okay? So I cannot put 700 million values in a single page or even 100 pages in the index. But that doesn't matter, because as we mentioned before, if my page size is based on the cylinder, and if the cylinder is 64 kilobyte, I'm getting one of these advanced hard disks, so I will probably have like thousands of entries in this page. And I will have still thousands of pages because I have 700 million entries in the column. But that's okay, because all of them now is on disk. And I'm not going to load all of them at the same time, because usually when I go through this index, I'm asking for a value, like select star from or x equal to 22, that appears here, 22. So I go to the directory, it will tell me go and load page 1 from the index, and from page 1 in the index, I will find that where is the row number 22 is stored on disk. So I go and load that. Okay, so let's see an example of inserting into the extensible hash table in order to understand how it works. So what you see on the left is a hash table, or an extensible hash table that has already been created. So I'm showing it to you after the insertion of 3 rows into the table. And as I mentioned before, the extensible hash table consists of 2 components, the directory and the pages. Now, let's kind of put things here into context. So we will start by doing this insertion of 1010 because we got a SQL statement, an insert SQL statement like the one I've put there on the top right, where the programmer is inserting a new tuple or a new row into the table. We have this extensible hash table built on a column in that table. So the column of interest here is the one that has the value, the new value 63. So say I'm building this extensible hash table on the column H. So when I get a new row inserted, I'm interested in the value of H in the insert statement. So let's say the value is 63. So we will proceed and do the insertion of this new tuple in the right page, in the proper location, based on whatever other column we're using to sort the table according to. After we've inserted this new row, we will take note of the file location or the page location on disk and the row number where it was actually the new row was inserted. So all of this is regular, like just common sense steps to do the insertion. Now what we're going to do next is we're going to start to work with the extensible hash table to also insert this new value, which is 63, along with a pointer to where this new row exists, okay, that has the value 63. So to work with the hash table, as I mentioned before, the extensible hash table, we're going to hash 63. So let's say the output of the hashing function is 10, okay? Now, there's no relation between the input to the hashing function and the output of the hashing function, except that it's a mathematical mapping from one input domain to some output domain. So we get the number 10 in decimal. What we're going to do is we're going to translate it to binary. So the number 10 in decimal translated to binary is 1010. This is actually what we work with when we try to do the insertion in the extensible hash table, the binary equivalent. Okay, what we will ultimately insert is the key being 1010 and the value being where that row is, which is the file name or the page address, comma, which row in that page. Now let's understand how actually the extensible hash table works. The extensible hash table depends on a number of variables or parameters that controls how it operates. The first one we're going to discuss is the I. Now the I value is telling us how many bits we are currently using to distinguish between the values or between the entries. Okay? So if the I is 1, then we're using 1 bit. And if we're using 1 bit, we only have 2 variations, 0 and 1. If we set the I to 2, that means we're using 2 bits, and consequently we have 2 to the I variations or combinations. So we have 0, 0, 0, 1, 1, 0, 1, 1. And if we set the I to 3, then we have 2 to the I again, so it's 2 to the 3, it's 8. We have 8 variations, which will be from 0, 0, 0 till 1, 1, 1. Okay? So again, the I is telling us how many bits we're using, and it's also telling us, this is what it's used for, how many ways we can differentiate between the entries. So if I have I equal to 1, I only have 2 variations, 0 and 1, or 2 possibilities, 0 and 1. Okay? So I will differentiate according to either it's 0 or either it's 1. If I have I equal to 2, then I have 0, 0, 0, 1, 1, 0, 1, 1. So I have 4 ways to differentiate between the entries, whether it's 0, 0, or whether it's 0, 1, or whether it's 1, 0, or whether it's 1, 1. So this is the role of the I. Now the J, and we only have, by the way, one I in an extensible hash table, which is associated with the directory. Now the J is another parameter that tells us how many bits are common between or across the entries, or for the entries in the same page. So if I set the J equal to 1, that means the entries must agree on the leftmost bit. If I set the J equal to 2, that means the entries must agree on the 2 leftmost bits. If I set the J equal to 3, then the entries must agree in that page on the 3 leftmost bits. Now notice I am keeping the J with every page. What that means is, it could be, for example, that in some page the J is 2, and in another page the J is 4. The difference between the 2 and the 4 is basically how many bits I'm using that are common. Okay, so again, I don't want you to get confused. I always get confused when I explain this, because they're very similar but not exactly. They're just used for different purposes, the I and the J. The I is a way to differentiate between the entries. The J is a way to group the entries. So if I say that J equal to 2, that means the leftmost 2 bits must be the same. If one of them is 0, 0, the rest has to be 0, 0. Okay? If I set the J equal to 3, then that means the leftmost 3 bits must be the same. So if any one of the leftmost bits is 1, 1, 1, then the rest must be 1, 1, 1. Okay? They have to all agree. Okay? If again I set the J equal to 2 in one page and the J equal to 4 in another page, that means in that page where the J is equal to 2, I am only requiring the 2 leftmost bits to agree. And if I set the J equal to 4, that means I am requiring that the 4 bits to the left must agree. Okay? So this is the I and the J. Now the other thing is, we have to have a limit, a fixed limit, on how many keys we can keep per bucket. So here the bucket translates to a page, and we go back to the same story we've discussed several times before. The size of the page is dependent on the size of the cylinder. So in a real extensible hash table, we would not have 2 keys per bucket as I'm doing here. I'm just putting a simple example to be able to illustrate the ideas, because I don't have lots of space in the slides. But usually the number of keys will be in the hundreds. Okay? So for me here, the number of keys per bucket or per page is just 2. Because I'm interested to show you what happens when it gets full. So I'm limiting that to a small number. Okay? Now, also, as a simplification here, I am also assuming that the output of the hashing function is 4 bits. In reality, obviously, it's not going to be like this. It's going to be either 32 or 64 bits. But that will just complicate my slides. So I'm just keeping it simple. I'm saying it's just 4 bits. And that's why I'm using small numbers like 10, which when it gets translated is going to be 1010. Okay? Now, let's try to understand the logic. How will this work? Now we have, what we are trying to insert, which is 1010. We go to the directory first. We always go to the directory first. And we look up the I. The I size is 1. 1 means we're going to differentiate between the entries according to the leftmost bit. Only one bit, which is leftmost bit. So I will go and check my entry, which is what I'm trying to insert, which is 1010. Now the leftmost bit there is actually a 1. So I will follow in the directory the arrow that is coming out from the cell that is labeled as 1, because this is where the entries that starts with 1 will go. So if I was inserting 0010, I would follow the arrow in the cell that has the 0 in the directory. But now, because my leftmost bit in my value I'm trying to insert is 1, I will follow the second arrow. I go and load this page. So the arrow here represents where is this page on disk. So I will go from following the arrow. I will basically look up the information in the cell to find out where is that page, which is I have labeled here as page 1, and I will load it from disk. And to my surprise, when I actually load it, I find that the page is full. I have in there 1001 and 1100. And the J is 1, which means that the entries here must agree on the leftmost bit. Only one bit, which is the leftmost one. Now, for sure they agree, as you see, that the first one is 1 and the second one has 1 also at the leftmost bit. But I have a problem now. This page is full and I need to do the insertion. So the only way to do the insertion is to create a new page. And I'm going to do that. I will create a new page. And the question becomes, what will go in the new page? Okay? Now, let's go on to the next slide to understand what's going on. So here I am creating the new page. And I am putting in 1100, and my new entry will go in the old page. So the old page will have 1001 and 1010. So let's try to understand what's going on here. Okay? We're going to set a rule. This is basically related to the systematic way the extensible hash table follows when we're actually creating pages. We will maintain a relation between the I and the J. Okay? The relation is as follows. The J should never cross the I. Okay? The J should never cross the I. Now, when we create a new page, someone has to point to the new page. So we have to check the I. Can we point from the I to the new page? Or the directory I mean. Can we point from the directory to the new page? Well, I is 1. And there are already 2 pages. And if you have I is 1, I have only 2 possibilities, 0 and 1. So that's 2 of them. And I'm using those arrows to point to the first page and the second page. Once I have the third page, there is no way I could insert an arrow in the directory with this setup to point to the new page. What that tells me is I have to increment my I. When I increment my I, making I equal to 2, I will have 4 variations, 0, 0, 1, 0, 0, 1, and 1, 1. And out of each one of those cells labeled from 0, 0 to 1, 1, I could have an arrow coming out. And consequently, I could have 4 arrows. But that's more than what I need. I only need now 3 arrows. So, what this is telling us, when we create a new page, we have to point to it. So we have to go to the directory and find out if we can actually point to it from the directory. If the directory already, if the directory arrows, if you'd like to say, if we would like to describe it like this, if the directory arrows are already occupied, pointing to other pages, then we have to increment the I to get an empty cell from which we point to the new page. And this is the picture that you see here. I have incremented the I to make it 2. Consequently, I'm actually now having 4 variations from 0, 0 to 1, 1. And I will adjust my arrows correctly. And we will talk about this adjustment, but I want you to look at the last cell. Is it pointing to the right page? And we said that the directory entries are used to differentiate between the rows or between the values. So when I is equal to 2, and we have 4 variations, in the last cell it's 1, 1, which means only the entries that starts with 1, 1 from the left should be placed in that page, in that new page. And that's why I have moved 1, 1, 0, 0 down to the new page, because I notice it starts with 1, 1, and when I increment the I get this 1, 1 cell, and I can point to it from to this new page, and that will hold only entries that start with 1, 1. Okay? Now, if you look at the second cell from the bottom, which is the one that's in the directory that says 1, 0, it is now pointing to the page that has 2 entries, 1, 0, 0, 1 and 1, 0, 1, 0. Both of them start from the left with 1, 0. And this is why I did this type of redistribution. I looked at the leftmost bits and I grouped the ones that are similar, which is 1, 0, 0, 1 and 1, 0, 1, 0 together, so that I can point to them from the directory from the cell that is labeled 1, 0, because both of them start with 1, 0 to the left. Okay? Now, if you look at the first 2 cells in the directory, 0, 0 and 0, 1, both of them are pointing to the first page that existed. And that one has the J set to 1. Now 1 means the leftmost bit must agree, and in this case it's going to be a 0. And if you look back to the directory, it's 0, 0, 0 and 0, 1, both of them agree on the first bit being 0. And the page also has the first bit being 0. Okay? Now, we're going to go over a number of issues here. I know that this is a little bit overwhelming if you see it for the first time, but I want to mention also about the incrementation of the J. As you noticed in the new page, the J is 2, and in the old page the J is 2. So what's the rule here to make things consistent? The rule is like this. When we create a new page, we increment the J. And we will never, we don't want ever to be in the situation where the J is greater than the I. So if we increment the J, we also increment the I. That's one way to understand it. Another way to understand it is like this. When I didn't have enough arrows, which is in the directory at the leftmost side of this slide, I incremented the I to get an arrow to point to the page. And since now I'm having an opportunity to differentiate between the entries, because the role of the directory is to differentiate between the entries by asking that the leftmost bits will be different between the cells. So between 0, 0, 0, 1, 1, 0, and 1, 1, the leftmost bits are going to be different, and this is a way we differentiate between the entries. And if we are able to differentiate between them, the more we differentiate between them, the faster actually we're going to do the search until we reach the O of 1 performance. Now, since I needed an arrow, I increased the size of the directory from 1 to 2, that's the I value. This is also an opportunity for me to go and group the entries in the old page and in the new page to do further grouping according to 1 more bit value in the J. Instead of making the J 1, make it 2. This will enable me to do better grouping and consequently better differentiation. Okay? So the I and J are tight in that sense. And there are 2 ways to think of it, that I'm starting by changing the I and consequently let's change the J, or I'm changing the J and consequently let's change the I. So they are tight. But the rule we will always stick with, to be able to do this differentiation and grouping, that the J should never cross the I. Now it is okay for the I to cross the J. In other words, it's okay for the I to get bigger and bigger than the J, but the opposite is not allowed. Okay? Because the opposite will create clustering and crowdedness in some of the pages and leave the other ones empty. And to prevent against that, we will set a rule that the I has to be at least as equal to the J, if not more than the J. So we are able to do more differentiation, and consequently when we track the J, or when we have the J tracking the I mean, which means that we keep increasing it every time we increase the I, we will also do grouping as well as differentiation. Okay, so we group related ones together by increasing the J from 1 to 2. Okay. Now, one observation here that often I get from students when they look at this running example, they would tell me, why didn't we increase the J in the first page? And here is the issue. those are pages on the disk, and we don't like loading lots and lots of pages. So we will only do local changes to the pages we are actually changing. In other words, I went to this second page that had 1001 and 1100, and I found that the page is full, so I created a new page and I shift the entries between the two pages now because I'm increasing my J to do better grouping. Okay? Now, I don't want to go and touch any of the other pages that belongs to this index, because if I keep doing that with every insertion, I'll be doing an O of n work. So I'm only changing the pages I'm interested in to do, or I have to change to do the insertion. Other ones are not changed, and that's why the J kept at 1 in the first page. In fact, we don't even go there. We don't change it. Okay. And the second observation, which is, students will always, find it a little bit confusing about the two arrows that are pointing to the first page. How do they know that in the first page that this is correct? How do they know that the first page has the first bit 0? Well, before we incremented from I equal to 2, when I was equal to 1, the first cell in the 0, in the directory on the left, was pointing to that page, so we know that this starts with a 0. Now we are doing the algorithm, so when we increment the I to 2, we also know that 01 starts with a 0. So it should also point to that same page, that same first page, because the first entry is 0. Okay? Now, how do we know that the J inside it is 1? Because if the J inside it is 2, this arrow actually is invalid, the second arrow in the new directory. Well, we are actually doing these insertions, we are actually doing these upgrades of the I and the J values. Okay, so if it was changed to 2, then we must have already been at I equal to 2. Okay, it does not make sense. So it will never be the case that J inside is 2, it has to be 1. By the way, what I'm not showing you here in these slides is actually the table. And what I'm also not showing you here is the arrow that exists beside each one of those binary values inside the pages that takes you to the page of the table. So besides 0, 0, 1 in the first page, there's an arrow that takes you to a specific page where that entry exists, okay? Or the key that gets hashed to the decimal equivalent of 001, which is 1 basically, okay? There's also a similar arrow that exists beside 1001, and another one beside 1100, and so on. Every one of those binary sequences has beside it an arrow that takes you to the page of the table that has the row, that has the value that gets hashed. When it gets hashed, you get the decimal equivalent of these guys. Now, let's look at this scenario. Okay, we're having now I equal to 2. We're going to follow the same logic. So I'm just going to repeat what I have been describing. Let's say I would like to insert 0, 1, 1, 1. I will check the I. It says 2, which means I have to use the first 2 bits to the left. So I'm going to use 0, 1. So I will follow the arrow to the page that, I will follow the arrow from this cell that is labeled 01 in the directory. I will go to the first page. I will insert there 0111 because I have an empty space. Am I going to increment the J or increment the I here? No, because I have space. Okay? I only start thinking about this business of incrementing the I and the J when I go to a page and the page is full. So I have to create a new page, and this will be an opportunity for me to adjust the I and the J if I need so. Now, and I will need so at least with the I. So I will insert 011, 0111 into the first page, and I'm happy. Nothing will change. Now I get the second value, which is 0000. Let's try to insert that. So again, I check the I. And the I is equal to 2, so I pick the first 2 bits to the left, which is 00. I follow the arrow coming out from 00 in the directory, and I go to that same page that already has 011. Now I have an issue. The page is full, and I must do the insertion. So I create a new page, and this is an opportunity for me to redistribute the entries between those two pages, the old page and the new page. And what I'm going to do is I'm going to increment my j, but I don't need to increment the I. Okay, why? Because I already have arrows coming out from the directory to the new page and to the old page. And that's what you see here. I created the new page and I'm planning to increment the j. So I moved 000 and 0001 to the new page, and I left alone 0111. Why? Because later on I will make the arrow coming from the directory from the 01 cell point to the second page, and the arrow coming from the first cell in the directory, the one labeled 00, to the first page. And again, when I create a new page, this is an opportunity for me to do better grouping. That's exactly why I move these two values in blue now to the first page, and I increment the j because I'm saying now that the first two entries to the left agree. In this case, it's 00. And the same thing for the second page. Okay? Any entry now that will go into the second page must start with 01. So this is now my example, my running example. Okay? Now, let's try to insert 1001. I already mentioned before at least 2 times that duplicates are always causing us trouble in the database world. Okay? Now, let's look at this value, 1001. I check the directory. Directory is equal to 2. So I look at the first 2 bits to the left, 10. That will take me to the third cell in the directory that's labeled 10 because it's the same value. I follow the arrow there, load that page, and I find that this page is full. So I create a new page, and I move in there the duplicates. Okay, so I have an old 1001, and beside it there's an arrow, obviously I'm not showing, that takes you to that row, and the second 1001, which is going to take you to another row, the arrow beside it will take you to another row, and these are duplicate values basically. Okay, now notice that we can set the rule when we create a new page and the j and the I are equal, we increment both of them, the I and the j. But when we create a new page and the j is less than the I, we only increment the j to match the I, and we don't increment the I. And the rule actually makes sense in terms of the number of pointers coming out from the directory, if you like to think of it in the other way around. Now, the impact of this is the following. I will increase my directory because, again, every time we create a new page, we increment the j to do better grouping, and consequently, we said the j should never cross the I, so we will increment the I so that both of them are the same value at 3, and we adjust the pointers. Okay? Now, when we said I equal to 3, it means I have 3 bits I'm using to differentiate between the entries, so that will vary from 000 all the way till 111. Okay, and I adjust the pointers according to what I have already described before. Now, I'm not going to show an example of deletion because deletion is just the opposite of everything I described. So I'm trying to save time in the lecture to cover more variations that are useful. But the point is, deletion is the mirror image, the mirror reversed image of insertion. Okay, so we're not going to do that. You should be able to do it on your own. So I'm just going to skip this. I'm telling you this so you can actually do it as an exercise. But let's go back to this business of duplicates. If you go back to the slide 26, you will notice that we actually were forced to increase the size of the directory because of a duplicate. Okay? Like the example here, 1101. And then I have an entry, another entry, second entry is 1100. If I get another 1100, that's just a duplicate. Okay? That duplicate makes me pay a price because I'm going to go and adjust my directory size and adjust the references and so on. So, And when we split here is really the crux of this issue. When we actually create a new page and increment the J, we're trying to do better grouping. But really with duplicates, there is no better grouping because they are the same. Okay? So it kind of defeats the purpose of what we're trying to do is incrementing the J all the time. Okay? To be able to do better grouping. So what we could do is we could avoid counting in the duplicates. We're going to still insert it, but we will avoid counting it in terms of the operations of the extensible hash table and just add the duplicates in overflow pages. Okay? So instead of doing it like what we have seen in slide 26, you can actually just add the duplicate in a separate page and link it to the entry that has the same value, like what you see here. And this is again an example of using overflow pages. So let's summarize what we know now. Extensible hashing is a very interesting scheme because it's showing us something that we haven't seen before, at least in your computer science curriculum, which is this ability of using the hash table without having to go through this sudden enlargements of the buckets, basically going from n to 2n to 4n to 8n to 16n to 32n and so on. Okay? And we're not doing any major reorganization, if you noticed. While in the case of the traditional hash table, when you cross the load factor, you're going to read all the entries in the old buckets and rehash them to the new buckets. We're not doing that at all here, if you noticed. We are just adjusting entries between the new page we just created when we find the page is full and the old page that was full, and that's it. The rest is untouched. So there is no major reorganization. Okay, and this is what I'm referring to here in the second bullet with no full reorganization. There is no reorganization here actually at all, except between the new and the old pages. Okay. Now also here, because we're not going from n to 2n to 4n to 8n, we don't have lots of wasted space, because when you go into traditional hash table from say 2n to 4n, let's say n was let's say you started from 1 to 2 to 4 to 8 to 16. Between 8 and 16 you have 8 slots empty and you're not using them. Okay, between 16 and 32, when you just enlarge the buckets, when you just double the number of buckets, between 16 and 32 you have 16 buckets that are not being used. Okay, over here this is not the case at all. Okay, we don't create a new page except when we go to a page and find it's full and we're trying to insert. So we create just one more page. Okay, so this actually could work for database engines. This type of a data structure, a secondary storage data structure, could work for database engines. In fact, it is one of two variations that are very popular to implement hashing mechanisms inside database engines. Okay. But what's the problems now? The first problem is we were forced, according to the way things went, to develop this directory to be able to go to a specific page only and kind of ignore the rest. So someone had to tell us, okay, go to this page inside this index to load from it the required information, which is what is the row in the table, okay, that you're interested in. So we needed a directory. But the problem is we're trying to do better than this. We're trying to do the same thing, but without having a directory. This level of indirection means that we're always doing one step additional, which is checking the directory first, fixing the directory if we need, and then going to our page, that belongs to the index. Okay? It might not sound like a lot, and I'm not telling you it's a major issue. Okay? But if we can get rid of it, then we'll even be doing things faster than what we're doing now. But there is something else that's actually quite problematic, which is how the directory is growing in size. The directory is growing as a power of 2. So it is growing very fast. The difference between 2 to the 6 and 2 to the 7, or between 2 to the 10 and 2 to the 12, is quite significant. So we run into an issue if we get lots and lots of rows inserted without any deletions. So basically, the directory might not fit in memory. At least in the case of embedded systems, where you have limited amount of memory, like, the computer inside your fridge at home, or your microwave, or your smartwatch. If you think of having a database there, and you're requiring, this behavior, and there's lots and lots of entries, then you might run into trouble, okay? And according to how it works, it doesn't make sense to page the directory and keep parts of it in memory and parts of it on disk, because the output of the hashing function could take you anywhere in the directory cells. Okay, so you really need to keep it in memory, and now you have a problem because it might not fit in memory. Okay, if you ended up enlarging it, say from 2 to the 32, and it was fine, and then you go to the next, which is 2 to the 64, now it's not fine, it's not fitting in memory. Okay, so you have now a problem. So what we're going to look at next is even a better hashing mechanism to build an index in a database that is even more superior than extensible hashing. But it comes again with its own issues. So what we will look at now is what's called the linear hash table, okay? Or it generally employs what's called the linear hashing mechanism. And it's built on two ideas. The first idea, we've seen something similar to it before with the extensible hash table, is that we're working with the bits to guide us what to do inside the hash table. But here, the bits will be manipulated or will be considered from right to left. So in the extensible hash table, if you noticed, we were always working from left to right. We always said, they agree on the leftmost bits. Now here, we'll always be working from the other side, from the right side. Okay? We're going to do the same mechanism. You get a key that you're trying to insert, you hash it, you get an output from the hashing function, you convert it to binary, and now you start looking at it from the right side. The second and very, very interesting idea, but very challenging to implement in reality, is that we will consider our buckets as adjacent to each other, and they are growing one after the other in terms of physical space on the disk. Which means what we're looking at here, as I mentioned, here is file grows linearly, which means that way at the left you have bucket 0, followed on the disk by bucket 1, followed on the disk by bucket 2, followed on the disk by bucket 3. So I'm magically, and we will talk about this magically, it's not magic at all, it actually will require some serious coding. What we are able to do here is to put the buckets, or basically the pages, one page beside the other. It's almost like, the cells of an array. They are contiguous, they are one after the other. There is no intermediate file from a strange application or something that we have downloaded before that will come in the middle. What you're looking at is the organization on disk. So the first thing we're going to look at is, how do these pages grow? How many pages are we going to get? And we're going to fall back to the issue of the load factor to decide on do we need to get one more page or not. And notice I'm saying one more page, and this is really what's interesting about this technique, that you always get one more page when you need that, and you will need that if your utilization or load factor increases above the threshold that we've spent some time discussing before. So again, the number of used slots, or the number of entries, divided by total number of possible entries I could put in. So let's say I have a linear hash table that I could insert 100 keys in, and if my load factor is 0.75 or 0.8, if we would like to simplify the calculations, then when I cross this value, I will get one more bucket, and I will do something that is very trivial in terms of reorganizing the entries to be able to drop below my threshold. Okay? Now, we will see a running example of this soon. Here is our running example. Now, again here, I'm not showing you the linear hash table empty because it's a trivial case, but I'm showing you after I've inserted 4 values. Again here, I get a key, I hash it, I get an output from the hashing function, I translate it to binary, and somehow I ended up inserting it in those pages that you're looking at. The first thing we're going to notice here is that, well, I have the pages numbered because, as I mentioned before, the pages are put beside one after the other, and they're almost numbered like an array cell. So the first one is page 0, the second one is page 1, the third one is page 2, and that will always be that number for that page. It's always going to be like, this is the second page, which is, you know, the one that has 1, 0 as a label. Okay? Now, so this is the first thing. Pages are put beside each other, almost like an array cell, or array cells, and they are numbered almost like an array. 0, 1, 2, 3, 4, and so on, except they are numbered in binary. Okay? Now, the second thing about this linear hash table, I'm also using an I variable that tells me how many bits I'm currently using from the right side in my data structure. I will stop there. I will not say this is used to distinguish or this is used to group. I would just say I'm just using 2 bits now since I is equal to 2. And again here I'm showing you a simple example with 2 keys per bucket as a maximum, just to show you what happens when it gets full. But in real life, again, this is going to be probably hundreds of keys in a single page. Okay? And I'm also assuming here that the output of my hashing function is just 4 bits, which is again trivial. Usually it's 32 and now more often it's 64 bits. I also have here, the last thing we are going to mention before I show you how it works is the M variable. And the M is telling me what is the last bucket I could work with currently. So I always start from bucket 0, and then I keep getting buckets, okay? So I would like to know what is the last bucket in my set of buckets. I know what is the first one. My first one is 0. But what's the last one? So here again, it's a simple scenario. The last one is bucket number 1. So I got bucket 0 and bucket 1. If M was like, the equivalent of, in decimal, the equivalent of 56, then I've got from 0 to bucket number 56. Okay? So M is telling me which one is the last one. Okay? Like, what is my boundaries in terms of buckets or pages on disk? Okay? I know where's the starting, which is 0, but what is the last one? And that's the M purpose. Now, what this should tell you is, if I say that I is equal to 2, which means I have 2 variations, I'm using 2 bits, so it goes to the 0, 1, 0, 0, 1, and 1, 1. But what this is telling you is, I'm not going to get, if I have I equal to 2, I'm not going to get the 4 pages whose address or whose numbers start from 0, 0 to the last one, which is going to be page number 3, in one shot. Okay? So it's not the case, I'm repeating this, it's not the case that when I gets incremented from 1 to 2, or from 2 to 3, or from 3 to 4, or from 5 to 6, that I will get all the pages up till, 2 to the I. So when I is equal to 2, 2 to the I is 4. So now I've got 4 combinations, or 4 pages possibly, from page 0, 0, or from page 0 all the way till page 3. That's 4 of them. But I'm not going to get all of them in one shot. I'm going to get them one at a time. And this is what you exactly see here in this illustration. Okay? Even though I is equal to 2, M is 0, 1, which means currently I have actually got all the way till bucket number 1. So I got bucket number 0 and bucket number 1. I didn't get bucket number 2, which is 1, 0, and I didn't get bucket number 3, which is 1, 1. Now the question is, when do I get them? And the answer is when I cross my load factor when I cross my threshold. I will get one more. So I will get 1, 0 first. And then I keep doing the insertions. And then when I find that I'm crossing my load factor, I will get the 1, 1. Now, what happens next? If I keep inserting values, I will cross my load factor again. So I'm going to get the one that follows. But then I have to increment the I to 3 so that I can get the one that follows. Okay? Which is going to be bucket number 4. Or the value is 4. Okay? Now, because 1, 1 is 3. So I'm going to get 4 bucket, whose index, if you'd like to think of it as index, is number 4. Okay? Now let's come to the very important part. If I say I is equal to 2, this means I'm using the two most bits to distinguish between the entries. Okay? So I want you to look at these 2 pages that I have now. The first page has, let's just look at the last 2 bits. The last 2 bits in the first entry, which is in page 0, and the top one, the whole thing is 0, 0, 0, 0. The last 2 are 2, 0, 0. Now, this makes sense. It makes sense that it goes in page 0, 0, because what we are going to do is we are going to put the entry according to the last 2 bits. So if the last 2 bits is 0, 0, we put it in page 0, 0. Now let's jump to the next page. In the next page, which is page number 1, the top entry is 0, 1, 0, 1. If you look at the last 2 bits, it's 0, 1. So it makes sense to go into the page whose address is 0, 1. But what about the second entry in page 0 and the second entry in page 1? Those two do not agree with the last 2 bits with the bits assigned to the page, or with the page address, or with the page number. Not address, but number. So if you look at the first page, the last row, the second value is 1, 0, 1, 0. The last 2 bits are 1, 0. They don't agree with 0, 0. Okay, it's not the same. Same thing here, 1, 1, 1, 1. I'm talking about this page number 1, second row. The last 2 bits are 1, 1. They don't agree with 0, 1. So what's going on here? You see, we're saying we are going to get one page at a time. And we only do that when we cross the load factor. But what happens if we get an entry who is destined or is supposed to go to a page we didn't get yet? We didn't add it to our set of pages we're working with. Okay? Because M is pointing before it. Now, we will do a trick. We will subtract a power of 2 from the last 2 bits in that entry to find a temporary location for it. So if you look at the entry 1, 1, 1, 1, the last 2 bits is 1, 1. We're going to subtract, so it's supposed to go to the page number 3, which has address 1, 1, which we didn't get yet. We will get 1, 0 first, the second page, and then we will get page 3 later on when we cross the threshold. So this 1, 1, 1, 1, the 4 ones are supposed to go to the page whose value is 1, 1. Okay, whose number is 1, 1. But we didn't get that yet. So what we're going to do is we're going to grab this 1, 1 and subtract the power of 2 from it. And that will, gives us the value 0, 1. The same thing for the second entry in page 0, 0, which is 1, 0, 1, 0. The last 2 bits are 1, 0. It's supposed to go to the 1, 0 page, which is we didn't get yet. So we subtract the power of 2 from 1, 0 to find the temporary location for it, which is going to be page 0, 0. Okay? Once we get 1, 0, once we get the page whose number is 1, 0, which is basically page number 2, okay? What we have now is page number 0 and page number 1. And once we get page number 2, we're going to go to page number 0, the page that has the value 0, 0 underneath it, and we will look up the entries there to find out if there are any entries that are there that were supposed to be destined, that are destined for 1, 0, but they didn't go there because we didn't get 1, 0 then, and we will move it from 0, 0 and put it in 1, 0. So in other words, we're going to move the entry 1, 0, 1, 0, and we put it in the second page, which is page 1, 0 when we get it. You will see that in the coming slides. And the same thing will happen with page whose number is 1, 1, which is page 3. Okay, so again we will move to it 1, 1, 1, 1, the entry 1, 1, 1, 1 when we get it. Okay. And this is pretty much is the only trick about linear hash tables. Otherwise, it's a straightforward, very straightforward idea. Now, also there is something here I would like to tell you, which is that in these lecture slides, when I was preparing them, I was trying to show up, the issue of finding a temporary page, a temporary location for an entry, because the page is supposed to be going to is not yet with us. But I don't really consider the load factor calculations exactly. Usually it's done in a systematic way, and either you check after you do the insertion or before you do the insertion. For example, here I am assuming that I will do the check after I do the insertion, which means I will always cross it first and then figure out, oh, I crossed the load factor, I crossed 0.75 or 0.8, so let's do the fixing. Okay, let's get one more page. Let's move n to be 10. Okay, but it's not done like that. I'm just showing it to you here this way because it kind of makes the explanation easier for me and for you. But if we're coding this, before I insert the last entry here that was inserted, say it was 1111, before I do the insertion, I will check up the load factor, and then it's going to be 3 entries and 4 slots. So 3 by 4 is 7. It's 70.75. So for sure, if I add the 111, it will go above that. So I don't do the insertion, I do the fixing first and then do the insertion later on. But I'm ignoring that here, okay? Because usually I get students confused. They tell me, if you were saying you were supposed to get the page when you cross the load factor, you already crossed it and you didn't get the new page. And my answer is actually, I'm assuming here I will cross it and then I will get the new page. I cross it by inserting the item, just again to show you all what I have been describing here. Okay, so you can say this is not exactly what will happen. What will happen is by the time we try to insert the 4th entry here in this view we're looking at, we get the new page first and then distribute the entries and then do the insertion. So I will get the 10, I will get m moved to 10, and then I will move 1010 to this page number 2, and then I will insert 1111. Okay. And this is the rule I have been describing to you. I have tried to code it as a formula. So if you're building this, if you're confused about how it works, then it becomes clear to you. So I will read it. It says, if h of k sub I, k is the key you're trying to insert, h of k is the formula that you're using to do the hashing, sub I are the I bits from the binary equivalent of the output of the hashing function. So if the output of the hashing function is 64 bits, translated from decimal to binary, or decimal to binary, then if I say I is equal to 2, I only pick the rightmost 2 bits. So if h of k sub I is less than or equal to m, which means the entry is going for a bucket I already have, then I will look it up at bucket h of k sub I. I'll just go there, okay? Which is the case for 0, 0, 0 and 0, 1, 0, 1. Okay, h of k is 0, 0, 0, 0. If I look at the first entry to the left, okay, top left, 0, 0, 0, 0. That's all of h of k, translated to binary. Sub I is just the last 2 bits, 0, 0. Okay, it is less than or equal to m. M is 0, 1. Yes, for sure. 0, 0 is less than 0, 1. So I go and look at the second line in red here, which says look at bucket h of k sub I, which means go to bucket 0, 0 to put the value there, or do the search if you're doing the search. Okay. Now, else means here that h of k sub I is greater than m. So this is going for a bucket that I don't have, okay, or a page that I don't have. Like for example, when I was inserting 1010 or when I was inserting 1111. If you look at the case for inserting 1010 as an example, h of k sub I is 10. Is it less than or equal to m? No, because 10 is bigger than 01, even in decimal and as well in binary. Okay, so I will go to, and this is really the tricky part, I will go, since I didn't get this bucket yet, I will go to the following bucket, some temporary bucket that I will, as long as I go to the same temporary bucket in insertion, deletion, and search, it's going to work. Okay, so it's going to be h of k sub I which is 1 0, minus 2 to the I minus 1. I is 2, 2 minus 1 is 1, so 2 to the power of 1, that's 2. And h of k sub I translated into decimal is going to be 1 0. That's the binary. The decimal representation is 2. So this becomes 2 minus 2, which is equal to 0. That will take me to bucket or page 0 0. Let's apply the formula on 1 1 1 1 to understand why did it end up being in page 1. The last two bits, h of k sub I is 1 1. You translate that to decimal, that's going to be 3. 3 minus 2 to the I minus 1, 3 minus 2 is 1. In binary, it's 0 1. That's why it ended up in page 0 1. Okay? This is just a temporary location for it, as I mentioned before, and this is how we find the temporary location, okay? To put it in. Now let's try to insert 0 1 0 1. And what we're going to do here, notice this is a duplicate. So let's just use overflow bucket. Okay? And overflow chains. How will I find the location to link the overflow chain? Well, using the same mechanism. I will look at the last two bits. It's 0 1. 0 1 less than or equal to m, which is h of k sub I, less than or equal to m. Yes, because it's the same. M is 0 1 and this is 0 1. So I will exclude the second line, which is look up bucket h of k sub I. So I'm going to looking up bucket 0 1. I will go in there and find there is already a 0 1 0 1. So I will not insert the duplicate to avoid crowding my pages, and I will link it with an overflow chain. Now in the textbook they go into a discussion, should you count this or not? And there are some examples in previous exams where I tell the students either you count it or you don't count it, just to see if the student is understanding how things work. Okay? So some approaches will tell you that don't count the duplicates, okay? And some will actually count the duplicates. Now, I followed here the guideline in your textbook, which is after every insertion. So as I mentioned before, as long as you're doing it in a systematic way, this is going to work. It will always be okay, and you'll always get the O of 1 axis. After every insertion, you check if the utilization is greater than 0.8 or 0.75. Okay? If it is, then get one more page. When you get one more page, you move the M. Okay? You move the M to the new entry. So for example here, when I got the new page, I moved, as I mentioned before, the entry that was supposed to be destined to this page. Now how do I know where to look? Am I going to scan all the pages? No. You only scan the page that you know is the temporary location for entries that were supposed to go to the new page that you just got. How would you find that? Again, just subtract the power of 2 like we have seen in the formula. So I know the address of the new page I'm getting, which is 10. So that translates to 2 in decimal. I will subtract it minus 2 to the I minus 1. That becomes 2 minus 2. So I will go and look on page 0. I will scan there linearly to find any entries that ends up with 10, and I will move it to the new page. Okay? And this keeps going on with the rest of the entries. Next, after some time, I keep doing the insertions. I will get the 1 1 page and I will move the M there, and consequently I will move the 1 1 1 over there. Okay? Now you might decide to consolidate your overflow chains because you have now a space inside the main page. Okay? Or you can just keep it in the overflow pages separately and link to the entry that they are duplicating or replicating as a value. So you link it directly to 0 1 0 1. Now, what happens when you cross the last page you can get with this binary value of 2? Okay, so basically you are at page 3, which is page 1 1. What you do is you increase the I. If you'd like to get the page after it, you increase the I. Now, the nice thing about this technique is nothing changes in the previous pages. You just append a 0 to the beginning of each one of the page numbers, and it's still going to be the same. So page 1, that's why I mentioned this before. Page 1 will always be page 1. I just append a 0 to the beginning of it, so the number does not change, whether binary or decimal. Okay, and page 10 becomes 010, which is the same as 10. Okay, and you keep doing that. Now notice when you move a new, when you get to page 100 and your I is 3, so you have to go to the page that would have entries that were supposed to go there with your eyes equal to 3 now. Then it wasn't 3, but that doesn't matter. So you're going to go and do the same computation we did before. So this is going to be 100, which is page 4. So it's going to be 4 minus 2 to the I minus 1. So it's going to be 4 minus 2. I is 3 minus 1, 2. So 4 minus 2 to the 2. So 4 minus 4 is 0. So you go to page 0 and find out any entries that ends with 100. When you inserted them there in page 0, they were in the correct location. It wasn't a temporary location. But now we will think of it as a temporary location because we are increasing the I to differentiate between the entries, and the impact of this is actually distributing the entries on the pages. So you're going to grab some of the entries in page 0 and migrate them to page 100, to page 4. Those are the entries that has the last 3 bits 100. Okay, and this keeps going on. This keeps going on. When you get page 1010, you're going to take these duplicates and put it there. Okay. Again, the impact of this is that we are gradually getting one page at a time, and when we get it, we migrate some of the values that existed in previous pages to this new page. So we are distributing the entries between the pages, and that means we are actually having less collisions because the pages are getting all filled up with some value as we go along, in the building up this linear hash table. So it's a great mechanism. No indirection, no wasted space, no full reorganization. Okay, you can still have some overflow chain, but there is one major issue with linear hash table that makes it a little bit challenging to implement, and this is the fact that we need the pages to be beside each other on the disk. Okay, because we got away from the directory. We got rid of the directory in the extensible hash table because we numbered the pages from 0 to some number, okay? And we are placing them beside each other so we know where to find them. If I know how to find page 0 and the page size is fixed, I know how to find page 1, I know how to find page 2, I know how to find page 3. It's almost like what we discussed in the first lecture, which is fixed length records, okay? If you know the size of one page and you know the starting address of that page, you know the rest. You can go to any page, okay? Because they are beside each other. But here is the problem. Who guarantees that the next page adjacent to you, the next space adjacent to you on the disk is going to be free so that you can put a new page there? There's no guarantee. The only way you can get this done is if you implement this on your own partition. There are really two ways to do it. Either do it for real and you gain a lot. Okay? It's just an incredible enhancement in performance, or you hack it or basically simulate it. Okay? Now, who does it for real? The Oracle database. How do you actually get that done? They actually require you to allocate a partition on your hard disk. So you extract it from the control of the operating system, you remove it away from the control of the operating system, whether it's Mac or Linux or Windows, and you put it under the control of Oracle. So you create a partition that no one has access to except Oracle. And then Oracle comes with its own file manager. So it divides the partition according to its own wish, according to its own desire, and no one else competes with it in controlling this space or storing anything on that space except Oracle itself. That enables the database to create a linear hash table, pages put beside each other on disk. If you don't have this idea, or you don't have this kind of implementation where you have your own partition and your own file manager to be able to do all this, then you cannot do it for real. You can simulate it, which is what many database engines do, like PostgreSQL, Postgres, and many other database engines. What they would do is they would create a big file, and they would create virtual pages within this file. But the whole thing is actually fragmented on the disk. Okay, it is not really the performance you expect, because virtually it looks like pages are beside each other. In reality, of course, they're not beside each other. They're scattered throughout the hard disk. Okay, so you're doing excessive I/O this way. How you actually create a hash-based mechanism. Now, again, the syntax for creating in a specific index type is not a standard SQL feature. So if you look at Postgres, this is how you do it. You say create index, you give it the index the name on this specific table, and then you say using, and you say hash. And between brackets, you specify the column you're building the hash on. Okay? Now, for other types of database engines, it might not even expose to you how you actually do it. They will do it either without direct intervention from you, or they would have their own syntax. So the takeaway is that a hash-based index should be used when you want to enhance the performance of SQL queries on exact value and do not care about any other query type. Why am I saying that? Okay, because remember, hash-based mechanisms are great except with one issue: the data is not sorted in any way. So exact value queries like select star from where x equal to 20, or select star from where age equal to 56, or select star from where name equal to Ahmed. You have exact value searches only. If that's the only thing you have, your best option obviously is a hash-based mechanism, because you're going to go there in O of 1. Okay? Regardless whether you have a billion rows or 50 billion rows or 10 rows, it's O of 1 because it's based on the hashing mechanism. But if you have, like, say, range searches, x greater than 10 and less than 20, there is no notion of ordering inside the hash table. So what the database engine could revert to is just a linear scanning of your entries in the page, and will not even use the hash index, because there's no way to use it except by traversing the whole thing from beginning to end. Okay, so consequently, with exact value queries, it makes perfect sense to use hash-based mechanisms. But for any other type of query, you'll have to worry about using hash indices, because most likely it's going to give you O of n performance. Okay, there's no way around that. And most likely, actually, most advanced database engines, most decent database engines, they would not even use the hash-based index, even if you tell it create a hash, based index on this specific column, and then you're running range queries on it. It will just ignore the index as if it doesn't exist, and it will load the pages of the table and start to do linear scanning. So you're better off, obviously, with a B+3. At least you can run it in log n. This is the reference for today's lecture. Okay, so I've linked for you the pages that you need to read to understand more of what I have described today, and you will get a lot of problems in the practice assignments.